So, the next talk is again by Ronald van Luijk, and he will speak about the rationality of the Pezzo services of high degree.
Yeah, except that I will continue a little bit from the previous talk because I didn't finish everything. And then, okay, so here's the lemma about Del Pezzo surfaces, namely that X is Del Pezzo surface over an else bracket closed field in this case. Then we've seen these exceptional curves. They're curves with self-intersection -1. And in fact, as soon as you have a curve with negative self-intersection, it's one of those. Then every curve, every irreducible curve with negative self-intersection is an exceptional curve. And the proof of it, where am I going to do the proof? Because I want to use this and I want to use this. Well, the proof will be up here only. The proof goes as follows. The adjunction formula tells us if you have a smooth curve C, so let's call this C, then the 2 times the arithmetic genus of C minus 2 is equal to the intersection of C with C plus the canonical divisor. And that's the same as the self-intersection minus the intersection of C with minus the canonical divisor. And this thing is ample. And that means that any ample divisor intersects any curve with positive intersection. So this is greater than 0. And if this is less than 0, and I subtract something here, then this is less than or equal to minus 2. And that means that in order the arithmetic genus is non-negative, so that means that we have, so this is, I should have started, so this is itself greater or equal to minus 2. So we have equality everywhere. If we have equality everywhere, that means that this had to be minus 1, and this had to be 1, and that's exactly what you need to have an exceptional curve. So every curve is exceptional, and that means that now what I claimed before the break that would follow does indeed follow, namely here's the theorem that's well known over algebraic closure, but apparently now we can prove it also over a separable closure. So if X is Del Pezzo, and we'll start abbreviating Del Pezzo with dp over a field that's separably closed, then X is the blow-up of P2 in at most, well, in 9 minus the degree of X as a Del Pezzo surface points in general position, or the degree of X is 8 and x is isomorphic to P1 cross P1. And the proof is already on the board, because I start with x. I blow down as much as I can until I have something that's minimal. Once it's minimal, it's either P2 or this Hirschsprung surface with n equals 0, then it's P1 cross P1. Or it's one of the other things for a Hirschsprung surface for n at least 2, but that cannot happen because that has a curve of self-intersection minus n after blowing down. So before blowing down, the strict transform has even smaller self-intersection, and that cannot happen because if it had a smaller, as soon as it had negative self-intersection, the self-intersection was minus 1 in fact. So you cannot get here. If you do get to P1 cross P1, I didn't write down it's P1 cross P1 blown up at some points. But as soon as you blow up one point in P1 cross P1, you can blow down two P1, right? On P1 cross P1, take a point. There's two lines going through it, because P1 cross P1 has these rulings, one in this direction, one in the other direction. Those lines have self-intersection 0 on P1 cross P1. So as soon as I blow up a point on the two lines that go through that point, they will become two curves with self-intersection minus 1. And therefore they are exceptional curves. And after you blow up, before they intersect each other in that point, after you blow them up, they become disjoint because they have different directions. So now you have two disjoint minus 1 curves, and you can blow both of them down, and then you actually go to P2. So unless you were P1 cross P1 itself, if you had to blow down to get there, you can go one step back, and then you can actually go to P2 also. So that's that. And I claim more. I said they're in general position. Well, first of all, if you blow up P2, if you end up with P2, you blow up a point, you blow up a point, you blow up a point. A priori, you might have to blow up a point that was on an exceptional curve that you got at a previous blow up. But that's not true, because if you are on an exceptional curve, it already has self-intersection minus 1. Now if you blow up a point on it, and the lemma that was there before, after the blow up, it becomes even less than minus 1. But that can't happen because every self-intersection that's negative is minus 1. So you're not blowing up points that were on an exceptional curve. So you're really blowing up a number of points on the P2 itself that are already all in the P2. But now I still have to show that they're in general position. Well, suppose that you have, well, I should then tell you what general position means. General position a bunch of points. I should also tell you how many. In P2, if you have a line, it has self-intersection 1. I should say it differently. The anti-canonical divisor. There's something we didn't say yet. I had before this blow up from x to y. If this was the blow up of y in the point P, and this was the projection, the blow-up map, then I told you that there's an exceptional curve here, and the self-intersection was minus 1, and the intersection with the canonical divisor on y is also minus 1. But here's another thing that's useful to know, namely, this canonical divisor on y I can relate to the canonical divisor on x. This is the pullback of the canonical divisor class on x plus e.
You should interchange y and x.
Oh crap, yes. I mean, yes, thank you. In my head they were indeed the other way around. Thanks. everywhere.
It's just a feature of Pezzo.
Maybe I should might have been more efficient to do it here. But, thank you. Indeed. So on P2, the canonical divisor is minus 3 times a line. So minus the canonical divisor is 3 times a line. And it has self-intersection 9. Each time you blow up, you get an extra E, which is self-intersection minus 1. It doesn't intersect this pullback. So the self-intersection of the canonical divisor also goes down by 1. It starts at 9, you blow up once, it becomes 8. But on the Del Pezzo surface, it's still ample, so it still has to have positive self-intersection. So you can blow up at most 8 points. Because the next time you blow up a point, it would get self-intersection 0 and it can no longer be ample. So if I'm going to tell you what general position means, I only need to tell you what general position means for at most 8 points. And here's what it means. If I have R at most 8 points in P2, they are in general position if, first of all, no 3 are on the line, no 6 are on a conic, and 3, no 8, are on a singular cubic with the singularity at one of the 8. So let's see why the points that we blow up if we get a Del Pezzo surface have to be in general position. Suppose that 3 of the points that I blew up were on a line. They start on a line. Well, that line in P2 has self-intersection 1. If I blow up 1 point, the strict transform of the line gets self-intersection 1 less, so 0. If I blow up 1 more point, it gets self-intersection 1 less again, so it's minus 1. If I then blow up the 3rd point, the strict transform of the line gets self-intersection minus 1. Minus 2. But that's impossible on a Del Pezzo surface, because on a Del Pezzo surface, all curves with negative self-intersection have self-intersection minus 1. So that means that that cannot occur. So no 3 are on the line. And for the other ones, you do the same game. The conic has self-intersection 2, 4. And if you blow up 6 points on them, every time the self-intersection of the transform would go down by 1, you end up also with minus 2, which is impossible. For the cubic, same thing. It starts with self-intersection 9. If you blow up 7 points, you get down to 2, and then if you also blow up a point where that has multiplicity 2 on that curve, then you have to subtract 2 squared. So you were already at 9 minus 7 was 2, minus 2 squared is also minus 2, is also a problem. So they really have to be in general position. Now it's also true, but I will not prove this, that if you have 8 points in general position and you blow them up, then you get a Del Pezzo surface. And for that, you have to show that the canonical divisor, the anti-canonical divisor, is still ample. And you really do have to do some work there to show that some multiple still gives you an embedding into some projective space. But it is true, but I will not prove it. Okay. So now let's look at the Picard group of these things. Oh, another thing you can see from this, by the way, is that if I start with a del Pezzo surface, and I take one of these exceptional curves, I blow it down, or I blow a bunch of them down, I get closer to this P2, then whatever I get, I can continue to blow down and still get a minimal surface, which will be a P2 or a P1 cross P1. But if I were in a P1 cross P1, I could go down to P2, and it would then, the thing in between, would then still be a blow-up of P2 at some points in general position. So that means that if I start with the del Pezzo surface and I blow down some number of disjoint exceptional curves, I still have del Pezzo surface. And another fact that I will not prove is that if the other way around, if you start with del Pezzo surface, you can blow down some points, blow up some points. And you might wonder, do I still keep a Pezzo surface? And the answer is yes, as long as you don't blow up a point that's already on an exceptional curve. Of course, you know now that if you blow up a point that's on an exceptional curve, you're in trouble. You're no longer getting a del Pezzo surface because the strict transform of that exceptional curve will now have self-intersection -2. But the converse is also true, that if you blow up something off the exceptional curves, you will get a del Pezzo surface unless you're already a del Pezzo surface of degree 1, because then you cannot blow up any more points and still expect the anticanonical divisor to be ample. And another exception, and it's an exception that's actually forgotten in Mali's book on cubic forms. If you have a del Pezzo surface of degree 2, we've seen it's a double cover of P2 ramified along a quartic curve. If you blow up a point on that ramification locus, you're also in trouble. So you have to avoid that one as well. Okay. So now let's look at the Picard group of these things.
I mean, they still have to be in general position, right?
Yeah, but that's equivalent with what I just said. I don't know who I'm looking at. I don't know who asked the question.
Yeah.
All right. Yeah, so what I'm trying to say is that that's equivalent. So the general position is a statement about what position they have to be in on the P2.
Yeah.
But if I've already blown up some points and I'm now looking at a del Pezzo surface, there's some number of exceptional curves on there. And I could wonder, well, I don't want to first blow them down and then look at the P2. I want a description in terms of that del Pezzo surface itself that tells me what can I blow up more.
Wait, you just explained that you can still like blow up the third point, and they could be, say, you blow up twice,
Yeah.
and then you take a third point, which comes from a line that already intersects, like passes through 2 points.
Yeah, and then you're in trouble.
Yeah, then you're in trouble.
And that's because on the line, after you blow up, so let's do this.
But it's still not be on the exceptional curve, this is what I'm saying.
No, but it is, because that line,
Yes.
after I blow up these 2 points, so this is the picture in the P2,
Sure.
I blow it up, I get still my line, but now this 1 point has been replaced by a curve. Before blowing up in the P2, this line had self-intersection 1.
Okay, so what do you mean? Okay, I see what you mean.
Right, and now this line, you already see it, but I'll tell it for the rest of for everybody else. This line, after blowing up once, has gone self-intersection 0, because we blew up a point on it, so the self-intersection went down by 1. If you now also blow up the other point, you get 2 exceptional curves, and now this strict transform of that line in P2 has become one of the exceptional curves, because it's a -1 curve. And that's why you're not allowed to blow up another point on it. So here you see only one part of what I just tried to say, is one reason why you're not allowed to blow up 3 points on a line. That's translated to saying that you're not allowed to blow up a point on an exceptional curve. And it's really, for this small part, equivalent. Okay, so what happens to the Picard lattice? I just erased this and I shouldn't have. So we have the Picard group of x, and the Picard group of x, if I blow up a point, x to y is just the same as it was before. This is the pullback of the Picard group of y plus one copy of z, namely whatever comes from that exceptional curve. And that means that if you start with P2 and you start blowing up a bunch of points, yeah, so now that x is the blow up of P2 in R points. For this statement, I don't even need them to be in mode 8. I also don't need them to be in general position. Then the Picard group of x is isomorphic to just the pullback of the Picard group of P2. Let's call that generated by L, with so L squared is a line, L squared is 1, plus a direct sum is 1 to R of Z times what I'll call here, without introducing, because hopefully from the notation it's intuitively clear what I mean. These are exceptional curves. And the intersection numbers are such that L times EI is 0, because you can also always choose an L that misses the points that you blew up, and the intersection numbers between the exceptional curves are just, well, they're minus the Kronecker delta. If they're different, they don't intersect each other at all, it's just 0, and otherwise it's minus 1. And that means that actually the intersection pairing on this free abelian group, finally generated, is non-degenerate. So that makes its Picard group into a lattice. And in fact, it means that we can, in terms of that lattice, so we can write every element, if I have any D, I can write it as A times L minus a number, yeah, a combination, an integral combination from 1 to R. And now if I want to know the exceptional curves, well, an exceptional curve is a curve, but it has a class, a divisor class, but it has negative self-intersection. So it doesn't move. There's only one curve in such a class, because if there were two different irreducible curves in such a class, they would have non-negative intersection with each other, and that would be the self-intersection. So negative curves don't move. There's at most one effective curve in such a class. And the classes, we can figure out. The exceptional classes are E squared, well, let's call it E. I'm going to look for, let's call it little e. I'm going to look for these exceptional classes. What is a self-intersection? Well, all these things are orthogonal to each other. So self-intersection is A squared plus the sum of the B squared times minus 1, so it's minus the sum of the BI squared. But I also know that E times the canonical class is minus 1. Oh, and this is also a minus 1. And what is the canonical class in terms of this? The canonical class on X is every time you just pull back the previous one plus E, we had seen before. So this is, in fact, minus 3 times L plus the sum of the EI. And if you intersect this with E, you get the L and the EI's are all orthogonal to each other again. So we obtain minus 3 times A minus plus the BI, plus the sum of the BI's, right? EI squared and the minus here. EI squared is minus 1, the minus becomes a plus. So now we have two equations in terms of the A and the BI's, and they're integers. And you can actually solve this. You can solve it in a smart way or a not so smart way. There's hundreds of ways to do this. One is just to say, okay, let's see how does it. You can use Cauchy-Schwarz. So the sum of the BI squares, the sum of the BI squares, well, let's look, write it like this. The sum of 1 times B, let's look at the vector 1, 1, 1, 8 ones, and another vector B1, B2, up to B8. These are two vectors, just in Euclidean space. And now I'm going to use Cauchy-Schwarz inequality on these, and it says that the inner product squared is at most the product of the two lengths and squared. So that is 8 for that one times the sum of the BI squares. But the sum of the BI squares is A squared plus 1, so this is 8 times A squared plus 8. And the sum of the BI's was 3i minus 1, so this is 3i minus 1 squared. So now we have an inequality on...
By 8 you mean R, right?
Yeah, well, if you solve it for 8, you've solved it for every R less than 8. So, yeah, for some cases you need some zeros at the end. Yeah. Yeah. So if you can do it for 8, you can do it for all of them. But now you have an inequality. This is a quadratic with a coefficient 9. This is a quadratic with a coefficient 8. Now I can do some undergraduate stuff. But there's only a finite number of A's that, integral A's that will satisfy this inequality. And in fact, you get that A is between 0 and 6. And for each A, you get a finite number of solutions for the BI's. And in fact, I can tell you exactly how many solutions there are. Namely, for R and a number of exceptional curves. If you blow up 1, 2, 3, 4, 5, 6, 7, 8 points, this is 240, 56, 27, 16, 10, 6, and 3 and 1. Am I doing that right? I think so. And tomorrow on Wednesday you'll see how this relates to root lattices, perhaps, or perhaps not. In any case, how that relates to the automorphism groups of these things. So a Del-Pezzo surface of degree 1, as you blow up 8 points, you have a Del-Pezzo surface of degree 1. The degree is always 9 minus the number of points that you blew up. It has 240 minus 1 curve. The cubic surfaces, I'd already said, many of you may have seen that it's P2 blown up in 6 points. That same statement comes in the context of cubic surface having exactly 27 lines. And indeed, the fact that E times minus the canonical divisor is 1, this is on a cubic surface or on any Del-Pezzo surface of degree at least 3, if the anticanonical divisor is very ample, it's linearly equivalent to the hyperplane section of the model in the anticanonical model. So you have a curve, and it intersects a hyperplane section in exactly one point. Well, then that curve, the intersection with a hyperplane section is the degree of the curve. So if the degree is 1, that means that it's exactly a line. So these things that we're looking at are really lines in that anticanonical model, unless you're in degree 1 or 2, where you have to take a multiple of the anticanonical divisor to get an embedding. So there's your 27 lines. And what are some of the solutions for those 27? For those 27, you get solutions like this. Oh, I'm erasing the equation so that you can not see that there's solutions anymore. But for instance, you have the EIs themselves. Yeah, the EIs themselves are exceptional curves. But also, if I take a line minus EI minus EJ, this divisor class corresponds exactly to the strict transform of the line that goes through the 2 points that these are the exceptional curves above. If we have that line, if we have a line in P2, and here I have a PI and a PJ, the pullback of that line to the Pezzo surface, to the blow-up, is the strict transform of this line, plus the exceptional curve above this one, and the exceptional curve above this one. So if I subtract those, I have exactly the strict transform of this line. So the strict transform of a line through 2 points is another one of those exceptional curves on which you're no longer allowed to blow up more if you want to get a Pezzo surface of even lower degree. Right? So that came up in the previous discussion as well. And also, you can take a conic. Yeah, so I'm saying a line, so this corresponds to the line through those points. There's also 2L minus E1 minus E2 minus E3 minus E4 minus E5. If I take a conic through 5 of the points that I blow up, conic is self-intersection 4 below. So if I blow up 5 points, then the strict transform of a conic through 5 points gives me an exceptional curve on the Pezzo surface, which corresponds to one of the 27 lines. So how many of these things do I have? If I look at cubic surfaces, I've blown up 6 points, so there's 6 of these. How many pairs are there among 6 points? 6 choose 2, that's 15. And how many quintuples do I have among 6 points? That's 6 choose 5, that's also 6. And it adds up exactly to 27. So there's my 27 lines. Okay. Well, and to describe all the 240 there, you get a long list. Okay. So what is the time actually?
15 minutes.
15 minutes, excellent. So on the schedule, it claimed that I was going to talk about rationality and unirationality the second hour of Del Pezzo surfaces of high degree. And high degree corresponds to blowing up few points. And I was hoping to do everything of degree at most 5. But I won't get to 5, but I'll get, so the definition of high degree will be a little higher for it to still work with the title of the talk. So here's a theorem. Let x be a Pezzo surface of degree b at least 5. So I will not prove this all today, but we'll just do it case by case. If x has a rational point, so if the set of rational points is not empty, then X is birational to P2. And you're thinking, well, I thought we were always the blow up of P2 in a bunch of points. That was over a separately closed field. So this is over any field. So here, the Pezzo surface over any field. And that is exactly what makes this theorem an interesting theorem. So apparently, if the degree is high enough, if you've blown up not so many points, then the surface is still simple enough, easy enough, to even over the ground field be birational with P2. And in fact, for some degrees, it's so easy, well, the proof is not always easy, but the truth is so nice that you automatically have a point. So in fact, for D in 5 or 7, the condition that there's rational points is automatic. And so now let's do this case by case. So let's start with degree, the highest degree, and the highest degree is just P2 itself, where you haven't blown up any points yet. So here's the proof, case 1, P equals 9. So that means that over a separately closed field, your surface is isomorphic to P2. But over the ground field, you might not be isomorphic to P2. Yeah, those are different things. So the question is, how do we prove that if there is a rational point, then we are isomorphic to P2 after all? And for that, I want to use, there's many proofs, there's many nice proofs, and to give a completely different approach, different technique than everything I've shown so far, I want to use Galois homology here. So the proof uses Galois homology. And if you've seen theory of forms of objects before, then you will recognize this right away. And let me sketch it in that generality also. If I have an object, so suppose I have an object, this is vague, I understand it. My object will be P2 if you don't like vagueness. Suppose I have an object Z over a field K. Now I can look at other objects that over the separable closure are isomorphic to Z. So other objects, I might have another object X also defined over K, such that there is an isomorphism of these objects over the separable closure. And let's give that isomorphism a name. And if I have such an isomorphism, well, there may be many isomorphisms. I can compose this with an automorphism of Z. But what I can do now, I can look at, so now if I have a sigma in my Galois group of a separable closure over K, I can look at the automorphism that's given by first the automorphism of Z over K's over the separable closure. This I first perform phi inverse, and I compose that with sigma applied to phi. And that's a map first from Z to X, and then back not through phi, but through sigma. So the Galois applied to Galois sigma applied to phi gives another isomorphism. that composition is an automorphism of Z. So this is an automorphism of Z over separable closure. We had to choose such a phi. So this automorphism is not well defined, because I might have chosen a phi that differed from this one by an automorphism of Z. But then if I take this combination, it differs. It turns out this is a co-cycle of the Galois group with values in this automorphism. And if I compose it with an automorphism, then I change that co-cycle by a co-boundary. So the cohomology class is well defined. So what I get is that associated, if I fix Z, then to such another object that's isomorphic to Z over the separable closure, I can associate an element of to such an X of which I know there exists an isomorphism, well, over the separable closure. This is bad notation because let me write this here, because over this, okay, sep doesn't go from X to Z, but the X then gives an element in the H1 of this Galois group with values in the automorphism group of Z over Ks. So that means that if we go back to our situation, we have a del Pezzo surface of degree 9, which over a separable closure becomes isomorphic to P2. So our Z is P2, and our X is our del Pezzo surface. In general, that means, well, so what is the automorphism group of P2? That's PGL2. So, oh yeah, PGL3. Very true. Thank you. So our del Pezzo, the surface of degree 9, X, gives an element in the H1 of the absolute Galois group. And the absolute Galois group means that group of the separable closure of the PGL 3 with values in Ks. And that's a big group. In fact, it maps by the definition of the PGL. The PGL3 is the quotient of GL3 by mu3. So this maps, if you take the short exact sequence associated to that, and then you take the long exact sequence, this maps to the H2 with values in mu3, which is the 3 torsion in the Brauer group of your field. But I haven't used yet that we have a rational point. So if I have a rational point, an X, it maps somewhere. And I might as well assume that it maps to the point 1, 0, 0, 0, 0, 0. And that means that phi maps that point to 1, 0, 0, 0. But because it's a rational point, sigma phi also maps it there. So that means that this automorphism fixes that 1.10000. So now I'm going to be very pictorial. These PGL3s, in fact, it's PGL3, but at this point we might as well prove that every, we're doing this for P2, but what I'm now going to prove is for every Pn, if I have a form of Pn, so a variety that over the separable closure is isomorphic to Pn, and it has a rational point, then it's already isomorphic to Pn. And you do exactly the same thing as here, except that you replace 3 by n plus 1. The PGL n plus 1 corresponds to matrices. They can have anything, but up to scaling. But now we know that the first column is going to map to that same point 1, 0, 0, 0. And if it's up to scaling, I might as well scale this to be 1. And that means that in fact,
Other than too many zeros for geometry?
yeah, it's because I said we might as well do it for Pn instead of P3.
A very general statement.
Yeah. So I switch from P3 to Pn. But that means that this x, actually the co-cycle I get gives me a class in the H1 of GK, not just the automorphism group of P2 over the separable closure, but the automorphism group of P2 together with that point. It's an automorphism of P2 that fixes that point. And that means that that group, now I'm being very sloppy in my notation, but that group is the group of matrices of this form. And I can send that to, so that automorphism group of P2 over the algebraic over the separable closure together with that point, I can send that to the matrix here in the bottom. And that's a GLN over K set.
So
And I hear so.
either the 2 is n or the n is 2 in that sequence, but this is a bit confusing.
Oh, you're right, sorry. I am mixing it up now. Thank you.
No, it's GLN.
That's one.
Yeah, so this is Pn,
No, it's fine.
this is
That's
Pn,
fine.
this is n plus 1, but the smaller block is n. And the kernel is, yeah, if you, the kernel is exactly what you get if in this block here you just have the identity matrix, and that group is isomorphic to just for each of these n places, one additive group of the K, the separable closure. So here I get the separable closure, if you wanted to put a plus here for the additive group, but also n times. And if that's an additive group, maybe this starts with a 0 instead of a 1. But these two, for these two, the H1 vanishes. Here I don't know what the theorem is called, and here it's Hilbert 90. And that means that the H1 of this middle thing also vanishes. So this X that ends up with a co-cycle actually a cohomology group, cohomology class in the H1 here, and then to the H1 there. It's already 0 here because this whole H1 is 0.
Although it's not a group.
Yeah, that's why I swallowed the group. I started
From
with
time to time.
I started with the group, and then I stopped saying it. Indeed, it's not a group because it's not a commutative group here, right? So it is 0. So, but how does it go with this whole story about objects? You end up with your X gives a co-cycle class, and it's exactly trivial when X was already isomorphic to Z over the ground field. And that apparently is the case. So X is already isomorphic to Pn over the ground field. And that shows that if you have a rational point, then any Pezzo surface, any Pezzo surface of degree 9 with a rational point is already isomorphic to P2. And the word that I should tell you when you do this, general n forms of Pn, so varieties that over separable closure become isomorphic to Pn, they are called Brouwer-Severi varieties. So Brouwer-Severi varieties with a point, they are already isomorphic to Pn over the ground field. And now probably I have no time left. Oh, that's very true. So surface of high degree in the title meant degree 9 only. And the low degree is tomorrow. Thank you.
Questions?
I was right about the time. I'm already too late, or am I confused?
Actually, you have 2 minutes. But
I have 2 minutes? No, I think this is a good time to stop. Yeah.
This is okay, maybe naive question, but if you do this for P1, there's a classical geometric proof, right? The coming to the point is P1.
Yeah.
Is there an analogous construction?
Yeah, yes, but it's fairly involved. You need to look at some linear systems and some blow-ups and some. There's a nice proof, but it's a bit involved. But it might have taken about the same amount of time. But I thought this was nice to see. Yeah.
So what's the idea of the geometric proof?
Well,
I mean, a general one.
so you start.
For P2.
So okay, so if you want a geometric proof, you start with your point, you blow it up. Now you have a Pn minus 1 in there also. You project to this Pn minus 1. You take a general enough hyperplane section there, pull it back to the blow up and push it down. Then you get a divisor on your surface, and you need to show that that the linear system associated to it gives you what you want. There's a little bit of bluff here.
No questions?
Thank you.